Recapping what we've looked at so far, we've talked about different kinds of light and the electromagnetic spectrum and how there are X-rays and gamma rays and different colors of light, and they are all at different wavelengths and different frequencies, but they all have the same speed. So we took that light and we then realized that light travels as both a particle and a wave, where you looked at with me the glow-in-the-dark circles and how those glow-in-the-dark strips light up because the light that goes through it has different energies. And so some of the circles lit up and some of them didn't. So that's proving there that light travels in a packet. Then we took that light travels in a packet and we tried to figure out, okay, here are these emission spectrums. And the hydrogen emission spectrum is different than krypton and neon and chlorine and nitrogen. So with those different emission spectrums, we saw different colors of light and different little segments or bands of color. And these gases emit those different colors because of the electrons that these particular gases have. The electrons get excited, and after the electrons get excited, then they leave their ground state, go to the excited state. Well, they're only there for so long, then the excited state electrons fall back down, and when they do that, they release energy and emit light. And so that's how we then see these different colors of light, or that's also how you can emit X-rays or gamma rays or any other kind of radiation. Well, now we're going to take that idea and look at these electrons and them dropping levels and try and figure out exactly what the atom looks like with these electrons. Okay, we already know the proton and the neutron are in the nucleus, but we don't know exactly where these electrons are located in the atom. So the first model that we look at is called the Bohr model of the atom, and it's named after Niels Bohr. And pretty much right after he had this idea, he realized that it was a wrong idea. But it is still a good place to start, okay? Just do know that it's not the right one, and we've known that for many, many years, as that this is not how the atom actually looks. Well, the Bohr model of the hydrogen atom is kind of like a solar system, okay, where we have these orbits that these electrons travel. So the electrons travel in orbits, or what we like to call clearly defined paths. These electrons that are in orbit have a specific amount of energy. The electrons that are further away from the nucleus have a higher energy, and the ones that are closer to the nucleus have a lower energy. Well, as they travel in these paths around the nucleus, they have a set track that they have. Very similar, like I said, to the solar system. Okay. Well, they also have, in the Bohr model, these different energy levels. Like I just said, an electron that is further away from the nucleus has more energy than an electron that is closer to the nucleus. So we have what are called these energy levels. And we've already looked at this before, but we're going to make sure that we mention it again, is that the lowest energy state is closest to the nucleus. And each one of these levels is separated by a large amount of empty space. And the higher in energy, the further away from the nucleus. So I'll have like a nucleus with my protons and my neutrons, okay? And then I have these paths that these electrons follow. So there's one path, there's another path, there's another path, okay? And as they travel around the nucleus, okay, the electron that's out here has more energy than the electron that travels that path right there, okay? Now what happens is that these electrons can jump energy levels. So if I have an electron here, it can jump up to the next energy level. And that's what we talked about with the emission spectrum. Okay? If the electron gains energy, it jumps up a level. If the electron loses energy, it falls down a level. And you end up with a picture kind of like this. Okay? If this electron wants to jump up a level, potential energy, or just energy in our case that we need to learn about, is gained as the electron is being pulled away from the proton. Energy was put in the form of light or heat. Okay? When the electron drops closer to the proton, light is emitted, and that's that yellow line right there. Okay? And we tend to call that light a photon. Okay, so we had some problems with this model, though. Bohr really only looked at the hydrogen atom when he was doing this. He decided to start very simple and then work his way out to the more complex atoms because hydrogen only has one electron. Well, it turns out that this does not work for atoms that have more than one electron. This orbit idea where an electron has a very set path that it travels on. And he based all of his work on emission spectrum energy values. And the light that was given off, those colors, okay, that have certain energy values. We're going to look at a flame test lab where the different colors of light have different energy values associated with them because they travel at different wavelengths. Okay, remember we talked about that E equals HV. So if I have a different frequency, I have a different energy. Well, these light values that he was seeing in these emission spectrums did not match up to the values that he was getting in his equations that he was using. So since these values that did not match up, he realized that his orbit idea was wrong and he had to try to get a different idea. Here are a couple of examples of things you may have seen before in physical science with the different electrons, those gray dots, traveling in a set path around the nucleus or those pink and green centers there. This is not how an atom looks. It's just very easy to visualize the atoms like this as opposed to what they actually are. So we're going to take a look now at quantum theory and the atom. And now we're going to get into actually where electrons are and how they travel around the outside of the nucleus. So the first one we'll look at here is electrons as waves. Okay, well we looked at this idea earlier about how light is both a particle and a wave. And electrons are very similar in that way. Instead of electrons being confined to a certain orbit, electrons are confined to a certain orbital. Okay, this is a space around the nucleus. We know this because electrons only have certain energy values based on the emission spectrum of those different gases that we looked at. So in reality, we have a nucleus. We have our little nucleus. These electrons travel in these set spaces versus set paths. It's not going to have a little path that it's going to follow like the solar system. It's going to be somewhere here in this general area outside of the nucleus. And the problem we run into here is what we call the Heisenberg Uncertainty principle. And I'm just going to kind of tell you what it is, and then I'm going to give you a very good analogy. Heisenberg uncertainty principle just says that it is impossible to know both the position of the electron and how fast it is going. I can't both know where it is and how fast it's going. And the analogy that I'm going to give here deals with a fan blade. So if you see this fan over here to the left of the screen, now if I start that fan up, are you going to be able to see exactly where every one of these 5 blades is? No, because what you end up seeing is a big blur. So if you look at a fan blade, okay, I could take, say, a stick, okay, and I could stick it in between the fan blades while it's going. Well, if it's a hardy enough stick, what's going to happen is it's going to stop the fan blade. And when it does that, now I know exactly where the fan blade is at, but I have no idea how fast this fan blade is going now because it's stopped. It's not moving anymore. Well, electrons work the exact same way, okay? I can figure out where an electron is if I hit it with something heavier. And what you do is you hit an electron with a photon. So you knock an electron off course with a photon, and you can see where it's at. But you no longer know how fast it's going. And if you do this enough times, if you kind of hit these electrons, I can mark the area, and you end up with these kind of crazy pointillism type pictures, okay? And so you end up with all these dots here in the middle. And what that means is that when I shot these photons into this atom, I had lots of times where I hit an electron. I have an electron that likes to hang out right around the center of the atom, right around the nucleus. Well then, as you can kind of see, here's a kind of a space in between here. Now you do see little dots here and there, which means that electrons still travel there, just not that often. And then as you go out again, you see another ring, which means when I hit those photons with these electrons, I got lots of hits right there. And so the electron also likes to travel right around the outside here, and that would be like our first or second energy level. So I might have an energy level here, and then I'll have another energy level here, okay? But these energy levels are not like floors to a building. They're not set, okay? They are spaces, okay? And they have these different shapes that we're going to look at here in a couple of sections. But for right now, all you got to know is that electrons travel in these set orbitals or set spaces, not on a set path. And I just want to kind of show this to you, okay? You don't have to memorize this by any means. You don't have to know how to use it. I didn't use this equation until I was like a junior or senior in college, okay? And it's called Schrodinger's wave equation. And what this wave equation did was it laid the foundation for the modern quantum theory. This was the equation that helped us figure out exactly where all of these orbitals were. And it mathematically describes a wave, and it mathematically describes where these electrons are. So all these different operators and wave functions and this constant, and even you got imaginary numbers in there, okay, helped us to figure out exactly how these electrons traveled and where they were and how our atom looks. So I just want to kind of give it to you. If you are a science person, you may have heard of this before. They like to make jokes about it a lot. Like about Schrodinger's cat and things like that. If you've never heard about it before, then that's all right too. Okay? And that's all for the model of the atom's electrons.